Imagine the soft hum of the cosmos stretching endlessly around you, a quiet ocean of starlight. And somewhere in that stillness, far beyond the spiral arms of our Milky Way, a giant star is taking its final breath. To understand neutron stars, we begin here, with collapse, with fire, with endings that give rise to impossible things. Massive stars, the ones many times heavier than our sun, spend millions of years burning hydrogen, then helium, then heavier elements like carbon, neon, oxygen, and silicon. At their core, nuclear fusion releases unbelievable energy, a perfect balancing act that pushes outward against gravity. Every second, a massive star fuses material, releasing more energy than trillions of nuclear bombs. Every second, gravity tries to crush it into nothingness. Fusion pushes out, gravity pulls in. The star survives only because these forces stay in perfect balance. But eventually, the core becomes iron. And iron cannot be fused to release energy. When iron builds up, even in small amounts, the delicate balance collapses. Imagine gravity suddenly winning the war. Imagine the star's core folding in on itself faster than anything you've ever imagined. In less than a second, the entire core, something the size of a planet, collapses to the size of a small city. The outer layers stall for a moment, then rebound, and the star explodes. A supernova. One of the most powerful events in the universe. So bright that the flash can outshine an entire galaxy for weeks. And in the heart of that explosion, among shockwaves and collapsing matter, a strange object is born. A core so dense, so compressed, so alien that normal physics bends and twists around it. A neutron star. This is not a poetic exaggeration. This is the real physics. The collapse is so strong that electrons are forced into protons, forming neutrons. The pressure is so intense that matter becomes a single giant atomic nucleus. Gravity becomes so extreme that time and space bend noticeably around the object. A neutron star is not simply a dead star. It is the most compact object in the universe besides a black hole, a place where nature pushes matter beyond anything we can imagine. As you drift with me deeper into the story, remember this. A teaspoon of neutron star material would weigh about 4 billion tons, more than every building in New York City combined. And yet, this impossibly heavy object is no larger than a city like Chicago or Mumbai, around 20 kilometers across. The star you once could not have wrapped your arms around is now something you could drive across, drifting in darkness, dense, silent, still. This is where our journey into neutron stars begins. To understand what makes neutron stars so extraordinary, we slow down. We zoom into the collapsed core. We move deep inside the most extreme material in the universe. Inside the collapsing star, gravity increases to unimaginable levels. Atoms are crushed. Electrons are squeezed so tightly into atomic nuclei that they merge with protons. This is called electron capture. Electron plus proton, aeroneutron plus neutrino. Millions of trillions of these reactions happen in a fraction of a second, and suddenly the entire structure of matter changes. The star becomes a giant sphere of neutrons, the particles usually found inside atomic nuclei, now existing freely, packed together in nearly perfect density. Let's explore the layers of a neutron star slowly and carefully. A. The atmosphere. A thin haze of superheated plasma. Temperatures, hundreds of thousands to millions of degrees. This layer glows in X-rays. B. The outer crust. a solid lattice of atomic nuclei. Electrons zip between them like lightning. This crust is thousands of times stronger than steel. C. The inner crust. Nuclei become strange, stretched shapes. Scientists call them nuclear pasta because they resemble spaghetti, lasagna, and gnocchi. These shapes appear because matter is being squeezed in ways normal physics never encounters. They might be the strongest material in the universe. D. The outer core. At this depth, neutrons flow freely like a quantum liquid. Protons and electrons float through it. Temperatures up to 1 trillion degrees immediately after birth, slowly cooling over thousands of years. E. The inner core. The most mysterious region in existence. We do not know exactly what happens here. Possibilities include quark matter, free-floating quarks, hyperons, particles made of strange quarks, boson condensates, superfluid neutron matter. This is the frontier of physics, where our laws may break or evolve. A neutron star is not just dense, it is superfluid, superconductive, quantized nuclear matter on cosmic scales. Imagine a liquid so perfect it has zero viscosity, a superfluid that can flow forever without slowing down. Now imagine that entire oceans of it exist inside a star. This is a neutron star.
Now we step outside the neutron star, into the space around it, where gravity becomes so strong that even time slows down. A neutron star's gravity is about 2 × 10⁻11 times stronger than Earth's. If you stood on its surface, your body would be flattened into a microscopic pancake instantly. Not because the star is malicious, but because its gravitational pull is overwhelming. Let's talk physics. Time, dilation. According to Einstein's general relativity, time slows down near massive objects. If you spent 1 minute near the surface of a neutron star, someone far away might experience 5 minutes or more. You would age slower. Time itself becomes stretched. Curved space-time. The neutron star bends the space around it so intensely that light passing by is pulled into curves. Nearby objects orbit incredibly fast. Even the star's own rotation can drag space-time with it, a phenomenon called frame dragging. Magnetic fields. Neutron stars have the strongest magnetic fields known, up to 1 quadrillion times stronger than Earth's. If you had a metal coin in your pocket, a magnetar's field, a type of neutron star, could distort its atoms, pull it apart, or rip it from your hand from thousands of kilometers away. A magnetar's magnetic field could erase your credit card from the distance of the moon. Spin. Most neutron stars spin rapidly because angular momentum is conserved during collapse. If a massive star rotated once every day before the supernova, the neutron star it becomes might rotate dozens or hundreds of times per second. These spinning neutron stars are called pulsars. They sweep beams of radiation through space like cosmic lighthouses. When the beam crosses Earth, we see a pulse. This pulse is so stable, so precise, that some pulsars keep better time than atomic clocks. You could set your watch by a neutron star. Let your breath slow. Let the night around you deepen. And imagine a lonely spinning star in the distance, a neutron star, rotating so perfectly that it becomes the most accurate timekeeper in the cosmos. When neutron stars spin, they often emit beams of radiation from their magnetic poles. These beams sweep across space like the light from a lighthouse. And every time the beam points toward Earth, we see a pulse. That is why we call them pulsars. But here's the astonishing part. Many pulsars rotate with such perfect rhythm that their timing rivals and sometimes exceeds the best atomic clocks ever built. Let's explore this slowly, carefully. A neutron star's magnetic axis is usually not aligned with its rotation axis. So as the star spins, its magnetic poles sweep in a circle, sending out beams of radio waves, X-rays, or even gamma rays. If one of those beams crosses Earth, we observe a pulse, and another one, and another one, every time the star completes a rotation. This happens with incredible stability. Some pulsars spin 10 times per second, 100 times per second, and the fastest known spins at 716 times per second. That means it completes one rotation in 1.4 milliseconds. Picture a sphere heavier than the sun spinning like the blade of a fan. Why pulsars are so stable? The answer lies in their structure. A neutron star is almost perfectly spherical. It's made of ultra-dense matter. It has no mountains, no shifting plates, no liquid oceans. Its interior is a quantum superfluid, and its crust is enormously strong. Because of this, neutron stars can rotate with unbelievable consistency. If you took two pulses and separated them by a year, the difference between their timing might be only a few billionths of a second. The pulsar PSR J437-4715, for example, keeps time so precisely that, over millions of pulses, the drift in timing is almost zero. Its stability competes with atomic clocks. These cosmic clocks allow scientists to detect gravitational waves, measure the shape of space-time, map the Milky Way, test Einstein's theories, and even find planets around neutron stars. Yes, some pulsars have planets. Old, cold, silent worlds orbiting dead stars. Now the universe grows darker around us, quieter, heavier. We are drifting toward the most extreme type of neutron star, a magnetar, a star with magnetic fields so intense they challenge imagination. If neutron stars are already extraordinary, magnetars are their wild, violent cousins. A magnetar is born when a neutron star forms with rapid rotation, a dense core, and a twist in its magnetic field. In a fraction of a second, it amplifies its magnetic strength into something terrifying and beautiful. Star, how strong are magnetars? To understand this, let's compare. Earth's magnetic field, 0.5 Gauss. A refrigerator magnet, 100 Gauss. Medical MRI, 10,000 Gauss. A typical neutron star, 1 trillion Gauss. A magnetar, up to 10 quadrillion Gauss. That's 1015 Gauss, the strongest fields known. If you came within 1,000 kilometers of a magnetar, your atoms would distort, your electrons would be ripped away, even empty space around the star would twist. Light would bend in ways impossible on Earth, and the vacuum of space could become polarized. This isn't poetic exaggeration, it is confirmed physics. Magnetars have crusts under immense strain. When their magnetic fields twist violently, the crust can crack, similar to tectonic plates on Earth, but far more powerful. These events are called starquakes. When a starquake occurs, a magnetar can release more energy in 1 second than the Sun produces in 100,000 years. One magnetar, SGR 1806-20, released such a burst in 2004 that it briefly changed Earth's ionosphere from 50,000 light-years away. Imagine that. A tiny star across the galaxy shook our planet's atmosphere. What magnetars teach us? Magnetars are important because they push physics to the limits. Their magnetic fields affect quantum particles. They show us how extreme pressures alter matter. They might help explain fast radio bursts. And they reveal the boundaries of nuclear physics. In the calm of this night, let yourself imagine drifting close, not dangerously close, but far enough to see the glow. A small, dark star, pulsing softly, holding unimaginable power. Now we slow down, even more, as we enter the most mysterious realm of all, the interior of a neutron star. This is where physics becomes dreamlike, almost surreal. The crust of a neutron star is only 1 to 2 kilometers thick. It contains ions arranged in a perfect crystal lattice. It has a breaking strain 10 billion times stronger than steel. It holds mountains, no taller than a few millimeters, but heavy as Everest. Experiments and simulations show that the crust is so tough that it could support small deformations. This leads to gravitational waves as the star spins, faint ripples in spacetime.
Deeper inside, gravity squeezes atomic nuclei into strange shapes. They stretch, merge, and rearrange into patterns resembling spaghetti, lasagna sheets, tubes, twisted gnocchi, honeycomb-like structures. This is not a metaphor. It is literal nuclear structure at high density, predicted by quantum and nuclear physics. Nuclear pasta may be the strongest substance known. Below the pasta lies a region unlike anything on Earth. The core is thought to contain superfluid neutrons, superconducting protons, ultra-relativistic electrons. A superfluid has zero viscosity, zero friction, perfect flow, quantum vortices arranged in neat arrays. Inside a neutron star, the superfluid rotates by forming millions of microscopic whirlpools, quantized vortices that store angular momentum. When these vortices shift or unpin, the star's rotation can suddenly speed up slightly. This is called a glitch, and astronomers observe them regularly. A glitch is like the star's heartbeat, a momentary jump in rotation caused by quantum changes deep inside. The inner core, the frontier of physics. This is the part that no telescope can see. No experiment on Earth can recreate it. No particle accelerator can match the density. Scientists think the inner core might contain quark matter, matter dissolved into its fundamental quarks, hyperons, exotic particles with strange quarks, color superconducting matter, a quantum state predicted by QCD, boson condensates, or something we have not discovered yet. This region is the greatest mystery in astrophysics. It holds the answers to
why neutron stars have certain maximum masses, how matter behaves beyond nuclear density, whether quarks remain confined or become free, and what happens inside collapsed, ultra-dense matter. In this slow night journey, imagine what it must feel like to drift towards such a core. Darkness wrapped in deeper darkness, silence layered upon silence. Matter compressed into its most fundamental form, a cosmic secret held tightly by gravity. Drift with me now into one of the rarest, quietest, and yet most powerful events in the universe. Two neutron stars, born from two different supernova explosions, orbit each other for millions, even billions of years. They spiral slowly, gradually, gently, like dancers circling in the dark. With each orbit, they release tiny ripples in the fabric of space-time, gravitational waves predicted by Einstein and finally detected a century later. These waves steal just a little energy from the system, and as energy drains away, the stars move closer, closer, and closer, and closer, until one day, after ages of spiraling, the dance becomes a fall. The two stars plunge toward each other in a final, breathtaking collision. What happens in a neutron-star merger? When neutron stars collide, physics becomes almost indescribable. Temperatures rise to billions of degrees. Matter is ejected into space at 20 to 30% the speed of light. The stars stretch and tear each other apart. Neutrons spill into the surrounding space. A hypermassive neutron star or a black hole forms in the center. The collision creates a burst of gamma rays, the most energetic light in the universe. For a moment, the universe flashes with radiance. But something else, something far more important happens. In the chaos of the merger, neutrons are captured by atomic nuclei rapidly, faster than they can decay. This is called the R process, rapid neutron capture. And it is here, in these violent collisions, that many of the universe's heavy elements are made. Your gold ring, your platinum jewelry, the iodine in your body, the uranium deep in Earth's crust, all of it was born in the death spiral of neutron stars. Not in stars, not in supernovas, but in neutron star mergers. This is not speculation. It was confirmed in 2017 when LIGO and Virgo detected gravitational waves from a neutron star collision, WG 1701817, and telescopes around the world saw the afterglow rich with heavy elements. We now know every gold atom in your body was once part of a dying neutron star. The light from a neutron star collision is called a kilonova, 1,000 times brighter than a normal nova, but dimmer than a supernova. Its color shifts from bright blue to deep red as neutron-rich material decays into elements. Blue light first, then purple, then a slow fading ember lingering in the blackness. A cosmic firework shining with the metals that will one day form planets, moons, and even living beings. As you drift with me through this quiet space, remember that every heavy element on Earth, every gold necklace, every atom of platinum in your bloodstream, every bit of rare metal in your phone, all of it came from stars like these. Dying stars, dense stars, stars colliding in silence. We are, all of us, built from the remnants of neutron stars.
Neutron stars are tiny compared to normal stars. They emit very little visible light. They are often billions of years old. They hide in darkness. So, how do astronomers find them?
The answer is simple but mysterious. By listening, by watching, and by feeling their effects on space-time itself. Most neutron stars that we've discovered are pulsars. Their beams sweep across Earth in a steady rhythm. Radio telescopes detect these pulses as repeating signals. A single pulsar might emit radio pulses, X-ray flashes, gamma-ray beams. But radio waves are the easiest to detect from far away. The very first pulsar was found in 1967 by Jocelyn Bell Burnell, who noticed a strange, perfectly repeating signal. At first, they jokingly labeled it LGM1, Little Green Men 1, because no natural signal was that precise. But it was natural. It was a neutron star, a cosmic clock ticking across the galaxy. Young neutron stars glow in X-rays. Their surfaces can be millions of degrees. Space telescopes like Chandra, XMM Newton, and NICER detect these soft X-ray pulses. NICER, mounted on the International Space Station, can even map the shape of spacetime around neutron stars by timing their pulses with microsecond precision. Some neutron stars, especially magnetars, emit bursts of gamma rays. These bursts can be so strong they saturate detectors across the solar system. Gamma-ray telescopes like Fermi, Swift, and Integral watch the sky continuously for sudden flashes. When neutron stars merge, they send ripples through spacetime. These waves stretch and squeeze Earth very slightly by an amount smaller than the diameter of a proton, yet detectors can sense them. LIGO and Virgo have opened a new way of seeing neutron stars, not by light, but by gravity itself. Sometimes a neutron star spins a little faster suddenly, a glitch. Astronomers detect these jumps and trace them back to changes inside the star's superfluid core. It's like listening to a heartbeat deep inside an object 1 trillion kilometers away. When neutron stars orbit other stars, their gravitational pull alters the partner's orbit. We detect these wobbles and infer the presence of the neutron star, even if we never see it directly. Some neutron stars show absorption lines in their spectra, signatures of atoms crushed by incredible magnetic fields. These fingerprints tell us surface temperature, magnetic strength, gravitational redshift, atmospheric composition. Every wavelength of light carries a clue, and astronomers piece them together like a cosmic puzzle. Each neutron star lives a long, quiet life. Once born, it slowly cools. It spins more slowly over time. Its magnetic field weakens, its pulses fade. So what happens in the end? A young neutron star glows fiercely in X-rays. But after millions of years, the light dims. After billions, it becomes nearly invisible. It becomes a cold neutron star. Still dense, still massive, but silent. Magnetars lose magnetic strength over tens of thousands of years. Their violent bursts slow. Their crusts stabilize. They become ordinary neutron stars once more. The star's rotation slows as it radiates energy. A 1,000-year-old pulsar might rotate 30 times per second. A billion-year-old neutron star might rotate once every few seconds. Eventually, it may stop pulsing altogether. If the neutron star has a partner, a normal star, it can steal gas from it. This process heats the neutron star, spins it up, strengthens X-ray emissions. Sometimes the neutron star is spun up so fast it becomes a millisecond pulsar, a star rejuvenated by stolen matter. Some neutron stars eventually gain enough mass from accretion or during a merger to cross the limit known as the Tolman-Oppenheimer-Volkov limit, about 2.2 to 2.4 solar masses. Exact values still uncertain. Beyond this mass, not even neutron pressure can hold the star up. The core collapses. Matter falls inward. The star disappears into a black hole. Silent. Invisible. Gone. Most neutron stars simply cool, fade, and drift forever. No light, no heat, just a sphere of frozen nuclear matter traveling through eternal night. A relic of a star that once burned brighter than anyone around it. Now, as we complete this quiet journey, let's reflect on why neutron stars are important, why we study them, why they fascinate scientists, and why they feel so mysterious yet so essential. Neutron stars let us study nuclear matter at highest density, quantum fluids, superconductivity, extreme magnetic fields, relativistic gravity. No experiment on Earth can recreate these conditions. Neutron stars are the closest thing we have to cosmic laboratories. Gold, platinum, uranium, and many others, all forged in neutron star mergers. Without these collisions, Earth would not have the materials needed for technology, planets, biology, even human bodies. We exist because neutron stars collided in the ancient past.
Pulsars allow us to detect gravitational waves, measure cosmic distances, test Einstein's theories, navigate deep space, study binary star systems. Their timing is so perfect, we use pulsars as potential galactic GPS beacons for future spacecraft. The energy from supernova explosions, events that create neutron stars, drives the evolution of galaxies. They spread heavy elements, they heat interstellar gas, they trigger new star formation. Neutron stars may hold answers to what matter becomes under extreme pressure, whether quarks can exist freely, how strong nuclear forces behave, what limits mass and density, whether exotic states of matter exist. They whisper secrets about the nature of reality itself. Above all, neutron stars remind us how strange and beautiful the universe is. Stars the size of cities, teaspoons heavier than mountains, fields that can tear atoms apart, collisions that create gold, clocks more precise than anything humans have built. They are the universe's poetry written in matter and gravity.